Okay. Hi, everyone. Welcome to our Vision and Language Seminar. Today, I'm very happy to introduce the speaker, Professor Chen Sun. Professor Chen Sun is currently an assistant professor of computer science at Brown University. He's also a staff research scientist at Google Research. Chen is a leading author of the paper VideoBird, the first bird-style model for video text representation learning, which inspired many recent uh, advances in video and language research. Chen and his colleagues also developed Vivid, which is a pure transformer-based model for video classification, video understanding in general. His recent work focuses on learning from unlabeled videos, which is also the main topic of today's presentation. And I am looking forward to learn more about this exciting research. Chen, you may take over from here.
Thank you so much. Thank you for the kind words and the introduction. So I'm Chen. So I recently joined Brown University as an assistant professor. And before that, currently I spent 5 years at Google. So the introduction talk about VideoBird and talk about Vivid. I won't talk about them today, but I'm happy to talk about them later on if you have any questions. So before I start my main talk, I want to give a brief overview of my research at Google. So I think during the first 3 years when I at Google, I'm interested in large-scale video understanding, but with fully supervised data sets like video classification or action recognition, action detection, and even tracking. And then there we show that the more data you have, the more annotated data you have, the better the performance, which nowadays I think is it's like a basic common sense for all our deep learning researchers. And I developed neural architectures for video classification and detection, such as the convolutional neural network based or like transformer based classifiers. And then I start to wonder, what can we learn from videos? I think this on the left is a keyframe from the atomic visual action dataset. And then from this dataset or from this just this single frame, we can actually recognize a lot of things like object detection, person, silverware, food. We can detect the actions. And we can recognize the basic human object interactions, such as person is holding a fork, eating food, and maybe is talking to another people. And then we can also do some basic guesses, like near future prediction, like after this finish the meal is likely to stand up. And then what else can we learn from the videos, or what else I want to learn from the videos? I think I want to learn something more like higher level, like the relationships. From we humans can infer that it's likely that the relationships of these actors are mom, dad, and kid, but I doubt like supervised classifier can do the same. And I want to do some of the temporal reasoning, like it's likely that it must be that the food were prepared by the parents. And then I want to do like longer future prediction, such as like after the meal, that is going to stand up and then wash the dishes maybe. And finally, long future prediction is more like not only visual signals, right? And we want to use visual common sense and other modalities to solve these tasks. And I think for the successful cases of like supervised deep learning, a lot of them belong to the so-called atomic concepts. And in the context of videos, they are typically the activities happening like within a short period of time. So this figure was taken from a book, and then the x-axis is basically time. And then from A to B or from A to C, you basically have a very short period of time, and then they tend to be more concrete and easy to be annotated by human readers. But as soon as we get to the longer term events, like they become more composite, they become more abstract and harder to annotate. So a natural direction would be to try to learn without explicit supervision. So I'm not sure whether I should call it self-supervised learning or unsupervised learning, because we actually have some of the natural supervision that come with the data we're dealing with, such as web images or web videos. So I will talk about that briefly later on. And then after recognition, I want to do predict and planning. Like, for example, my favorite case is since Unlabeled is that about cooking, like how to turn a raw egg into different dishes like omelet, scrambled egg, or fried egg, right? And we can learn from videos, and we can treat that as a common sense knowledge about what an egg can be turned into. And then we can also turn our observations, such as the trajectories of human beings and vehicles, cyclists, into like a prediction task. And by predicting what may happen in the future, we can then do the planning, such as we want to make sure that a self-driving car won't hit a person. And for that, I also want to transfer what has been learned in this context of this talk, what has been learned from videos, from these passive observations to prediction and planning tasks. Okay, so here's the outline of the talk. So I will briefly introduce three recent ICCV papers this year. So they cover basically the spectrum of the topics I'm interested in. So from recognition, learning video representations, and prediction, learning temporal dynamics, and control, like vision language navigation. So in the topic, in the title of the talk, I mentioned learning from unlabeled videos. So the first two parts are indeed learning from unlabeled videos, but the third one is more like learning from automatic generated demonstrations. So you will learn at the third part of my talk. Okay, let's start. And then I think everyone in this meeting knows, or maybe hopefully is interested in using speech as an instructive knowledge as a source of supervision, right? And then we have diverse source of such instructional videos on the internet, such as tech talks or cooking videos or how-to videos. So we all know about that. And then I think beyond what has been done with web images or web videos, actually, I think we can consider all those multimedia or multimodal contents as a whole as a learning source. They can come from YouTube and they can come from Wikipedia. So I'm a football fan, and you can see that on Wikipedia pages, you got the captioned photos, you got whole paragraphs of text describing what's going on, and even books, books designed for the kids. They're picture books, and they have illustrated text as well. So those can all be sources for our multimodal models to learn. And for multimodal learning, I guess we want to encode all those different modalities with a unified model. And such modalities can be text, like words, can be audio, like waveforms, can be images or videos, such as pixels. And then I think two years ago, we made an attempt like Unlabeled. It's, I think looking back, it's kind of a very intuitive idea. Like you want to do sequence reconstruction. You try to mask out some of the tags or some of the keyframes and then predict what's going on. And that's provides a natural supervision to establish correspondence between different modalities. And then by training this on unlabeled videos. So I need to mention that the videos here, they were just cooking videos on YouTube, and then we run off-the-shelf ASR extractor to get the speech transcripts, and we use that as all the information. And after training on 300,000 cooking videos, we can use it for recipe illustration or captioning without without any like downstream fine-tuning data. And we can also do zero-shot classification. The key idea is very similar to what GPT-3 did with their like prompts, right? But they were doing it with text-only data. So here we are trying to repurpose the task as image or video conditioned prompts, so that it naturally behaves as a classification or object classifier or action classifier. And then we observe that given enough data, it can achieve on par performance with fully supervised data. So these are some of the preliminary work that I did. And going forward, I have a roadmap towards like video understanding. So I would like to start from like object representations and their interactions, and then using those to build scene representations, and then adding time signals to have short video representation. And that shouldn't come from just like pixels, but also other modalities to get multimodal representation. And we want to like do the prediction to predict what may happen in the future to capture the temporal dynamics. And finally, we want to generalize the whole framework to longer videos, or my dream is eventually to movies understanding, which is the, I think, holy grail of the video understanding. And so that's, and Videobird and many other like papers after Videobird kind of belongs to multimodal learning. And a drawback of Videobird is that they assume the existence of already extracted visual representations or linguistic representations, but those may not be readily available or maybe come from a completely different domain. So they need to be learned. And here I describe how I plan to learn it from unlabeled videos. So I assume
can I have a question? Yes. Can you go back? Then go back again. So for the video, so this is using the Videobird for zero-shot classification.
Mm-hmm.
Can you provide some more detail about how the Videobird can be used for zero-shot video classification? Because I think the input is the caption plus the video frame, right? Then how this can power zero-shot so classification? Yeah.
That's a good question. So I think the input, during pre-training task, this is the input. We have the captions and we have the RGB frames. And when we transfer this model to a downstream task, so in this case, I think it's UCook2, we only use the pixels. And basically I'm not sure if you can see my cursor, but we only provide the text inputs, the RGB inputs to Videobird. And then for the text input, we have a template sentence or a prompt, like somebody is doing something. And then we mask out a doing and then something. And then let the model to predict what the mask, the verbs and objects are. And that essentially behaves like an action classifier or object classifier. Is that clear?
Yeah, thank you. Yeah, that's very interesting. So you mean, so indeed you trained a multimodal bird, but then in order to do zero shot, you just input the video frame or just input the template so that you can do zero shot. Okay.
Yes.
Thank you.
Yes. That's a great question. Actually, I'm also interested in after we do multimodal training, and then if we only applied to language understanding tasks, would that additional information from the pixels be helpful? So I think the answer based on one of our student researcher is that it's TBD, it's unclear yet. So we are actively working on it. Okay, so going back, I think I assume everybody is familiar with contrastive learning, or like if SimClear, CPC, MoCo, or instance discrimination. So if not, no worries. I will use this panda example to illustrate it. So the idea is very simple. So you have a database of images, and then you want to learn a visual encoder, which can be a transformer or it can be a convolutional neural network, to encode the original image and the randomly augmented image. In this case, it may be a random crop. And then you also use the same encoder to encode all the images in the database. And then your training objective is then to be like making the representations of the different views of the same instance or the same image similar than all the other like images in the database. And then by doing this discrimination objective, basically people have shown that they are able to achieve very competitive performance when transferred to like downstream image classification, object classification, video classification tasks. And for videos, people have done the same. I think this was work done by my colleagues at Google. So it basically like generalized the SimClear framework to videos. And then you can see that when they try to construct different data augmentations, they not only do like spatial augmentations that were designed for static images, they also do like temporal like augmentations by randomly sampling different segments of the longer video to construct different views. And they want the representations come from the same short video to be similar than the other videos in the dataset. So it also works, I think it's the state-of-the-art for self-supervised video representation learning when transferred to a lot of downstream video classification tasks. So very impressive. Okay, so however, I think there's an unanswered question. It's like, why does SimClear or like all those contrastive learning works, and what should consist the positive pairs? I think for images, the intuition, at least to my understanding, is relatively clear, is to preserve the identity with the semantic labels of the objects. So ideally, you want the different augments of the same image to contain certain parts of the same objects. And then by trying to learn the encoder to associate them together, it basically, you force the widget encoder to encode the semantic information, such as this is a panda. And for videos, to me, it's less clear. So we can do the same thing. We can always generate different spatial augmentations, or we can, in this case, temporal augmentations. So these are the frames from the same video, but maybe 5 seconds apart, trying to cut them orange. And what may happen if we try to use a standard contrastive learning framework on those like different views of the same video? So the standard framework is basically trying to take these two images and map them to the same latent representation in the representation space. And then the idea is that we want to like let the representation invariant of the noise. And in the image case, it would be like a random background jittering, those kind of stuff. So, okay, if we do that, that's great. Like what has been encoded is trying to associate them together. And in this case, the encoded information are likely to be like the color, like because they are all orange, and maybe the shape of the knife because it's preserved in both keyframes. But then the noise, like what differs from those two keyframes are the shapes. Like one is like whole orange and the other is cut orange. And then if our representation by design like lose such information, invariant of such a so-called noise, then we lose the shape information, and then as a result, we cannot do like simple tasks like error of time prediction, like which happens before and which happens after. So this natural view construction approach like induce undesirable invariances. And how to like deal with such undesirable invariances? So one previous work from UC Berkeley, they basically try to mitigate this issue by constructing many pairs of views, and each of them, they leave one data augmentation out. So that representation is still aware of such data transformations. But this may not scale well if we have many different interested data augmentation types. And another solution is basically we try to learn an equivariant representation. So equivariance here means that if you do a transformation in the input pixel space, then you can do basically corresponding representation in the learned feature space. But you don't, so invariance is basically a special case of equivariance. But this, I would like to argue that it's not necessary for many tasks. Our solution actually is quite simple. It's like we try to still use the contrastive learning framework, but we let the projection head to be aware of the augmentations between the different views. So instead of doing this standard like contrastive learning, we basically, we basically allow the representation of the two keyframes or two segments of videos to differ in the representation space. But then after we provide additional data transformation, we want the transformed representation of the second view to be as close as to the first view as possible. So actually the motivation is trying to learn an implicit prediction model based on the temporal transformations. And then if the information are shared between the two views, such as color, it can still be preserved in our representation, no issues. And if some of the information are predictable, such as temporal dynamics, they can also be preserved, such as shapes. And then we also have the benefit of like robustness from the contrastive learning, because unpredictable noise is still like still considered noise and being discarded, such as random camera motion. And then we show that this particular framework, it's a generalized form of some special cases, such as wheel invariant coding, which is like simpler, and wheel predictive coding, such as CPC. And to make it composable, basically we turn the fully connected projection head into a transformer. And then the transformer is not part of the visual backbone. It's only responsible to encode a sequence of parameterized like data augmentations, and then trying to encode such sequential information, and then use transform the input encoded visual representations. And here, the yellow blocks, they are the data augmentations from the two views. And then the input to the transformer is basically the delta between the delta of data augmentations. Okay, so this is our framework. And then we applied a bunch of data set. And in particular, something special is this something data set. It's an object-centric data set.
Sure. Question on the previous slides.
Sure.
Could you explain what you really learn in this slides? I'm a little bit confused.
Okay, so I'm learning the widget encoder F here. And I'm also learning the transformer projection head G during training. And then they jointly try to minimize the contrastive loss. And during inference time, we only like transfer the representation of F. So the transformer and the data augmentations are completely thrown away.
But do you learn the augmentation, or the augmentation is not learnable?
The augmentations are randomly sampled, but the encoding of the augmentation is learned. For example, if for time shift, if we assume the time shift is discrete, like by k-frames, I basically need to learn a lookup table of like maybe 100 entries, which correspond to a time shift of up to like 100 steps. Is that clear?
So I understand you learned the visual representation and also the transformer head, but from here, basically the augmentation, you represent the augmentation as a Gaussian distribution, maybe a distribution, maybe not Gaussian, a distribution over the time domain. And you're trying to estimate that distribution and figure out what's the best distribution for each video and as the augmentation. So I want to understand on the augmentation part what you learn.
I don't learn the distribution. I learn encoding of a particular time shift sample from such distribution. Is that clear?
So you encode this augmentation, and what does encode the representation means? What's the meaning of that? Tells you.
Sure.
So is that tells you something? So with this information, you are more likely to find the best augmentation or in terms of the time shift?
Okay. So sorry, I hear some echo. So
I turn off my.
Sure. So I don't learn how to sample from the data augmentations. I assume they are already given, but the augmentation encoder is trying to capture like if the two frames or two views are adjacent in time, then the encoded data augmentation should be different from if the two views are far away from time, far away in time. And similarly for crop, if the spatial location are far away, they should be different than like adjacent crops in the same video. And but the distribution of the data augmentation itself is completely like random. It's basically sampled from a already known and fixed distribution. Is that clear?
Okay, so basically you learn a mapping from the input videos and to the augmentation. And so then basically your augmentation adapt to the input. For different input, you have a different augmentation encode output. That will give you different data augmentation for the second pass of the. Yes. Okay, cool. Thank you.
So if we only, that's a great question. And if we only consider time, then basically the augmentation encoder E and the transformer head G is basically trying to learn a forward prediction model in time, in the latent space. So that's what it is.
Okay, so basically this shows there is a relationship between the input and the proper augmentation should be used. Is this correct?
Yes.
Okay, cool. Thank you for clarifying.
Cool. Yeah.
Yeah. So the output of the augmentation encoder has the same dimension as the token dimension, right? I want to know how do you combine the FVJ and the E delta T and E delta L and the class token. So they have the same dimension, right? Then you just use the class token to summarize all the informations.
Yes.
Before feeding into the head, right?
Yes.
Okay. Thanks.
Yeah. Okay, so I will continue. So this data set is kind of special because it's object-centric. And if you look at the classes, they are quite fine-grained with respect to like simple temporal reasoning, like picking something up or putting something down or pretend to put something down. So you really need to understand the error of time, the temporal information to solve this task. And here are some of the results. Like I first show like the augmentation encoding actually helps over the no augmentation. And the no augmentation is basically corresponding to the SimClear baseline, but we train it on this video data set. And then for crop and for crop, we also study some of the regularization, which in terms of dropout, and show that a slight regularization is helpful. And for time, we actually study how to like parameterize the data augmentations before we encode them. So we try to encode the sign of the delta t, basically the error of time or the delta t itself. And then we show that the more information the projection head has, which is the concrete delta t, then the better the performance is. And then another interesting task is that we try to, instead of just directly reporting classification accuracy, we just use the learned representations to solve a simple task, which is trying to predict the error of time. So given two randomly sampled video frames or video clips from the same video, we want to predict which one comes first. And then we show that basically, as we suspected, without the time encoder, just using the SimClear objective, which is supposed to be invariant of temporal augmentation, the performance on time offset prediction classification is actually very bad. And then if we use provide error of time, then it's better. And then if we provide the delta t, it almost achieves perfect error of time recovery performance. So I think this is pretty interesting. And then like the augmentation encoding can be composed. Like we can, so in this particular case, we only consider crop and time. And then we show that combining them leads to better performance. And here is a like per class comparison of the temporal, the classes that benefits the most with our like proposed framework that encodes time and hurts the most. So if you look at those blue classes, which benefit the most, they are typically like quite fine-grained with respect to temporal reasoning, such as lifting something up completely, then letting it drop down. And then for those in red, which barely helps or even hurts, you can see that error of time barely matters for those. And here's a Disney plot, and on the top is our proposed model, and on the bottom, no encoding is provided. And then we zoom into a few like pairs of classes, and then we see their distribution. And indeed, our model is better learn representations that better separate out the representations, projected representations from different classes. Okay, a side note, are there guiding principles on how to select views? So for the sake of interest of time, so I wouldn't go into details, but so we have an intuition basically, like which we call infermean principle. It's like, suppose the downstream task is Y.
Hi, Chen, may I ask you a question about the previous one?
Yeah.
So I'm curious if you have done a very simple baseline, which is just use that input to predict the Gaussian distribution of the time shift. And so given an image, given a video clips, and you look at that, and there's a Gaussian distribution over, so over the distribution at mean, you probably have similar, but not identical content. But after maybe 10 seconds and totally switch the view and you have no clue. So, and if you only predict that Gaussian distribution and use that one as your augmentation, and how bad it is.
It's actually pretty bad. And I think it's one of those earlier works in the self-supervised learning community, like predicting rotation of images, or like trying to solve the temporal jigsaw puzzle, like reordering frames. And in this particular case, you mentioned the temporal shift, and they tend to like suffer from the shortcuts, and they are not. I think I forgot about the exact numbers, but I think for this data set, maybe 15 or even 10 top one accuracy. So it's pretty bad. Does that answer your question?
So, okay, so if that is pretty bad, and what's the significant difference between your model, your encoder, and to that one? What's the difference?
So I think our framework incorporates that predictive coding, or like a pretext task with this view invariant coding. So I think in that particular formulation, their representations are not encouraged to be robust against different other type of data augmentation, such as color jittering or different random crops, which turns to be critical to learn robust visual representations. Whereas in our framework, it's just natural. So you just need to specify the augmentations you want to encode. And for other augmentations, you just ignore them and do not pass them to this like transformer projection head. And then as a result, for those you pass into the transformer head, your representation should be aware of them. And for those you do not pass, your representation is supposed to be robust against those. So it's trying to combine the best of both worlds. And also that can be like kind of partially observed by our empirical study. Like we tried beyond crop and time, we also tried a bunch of different like other augmentations, but they are not helpful and sometimes even hurts the classification accuracy. And in the original Sinclair paper, they basically studied they need to do certain combinations of data augmentations and let the representation invariant of those in order to get competitive performance. So I think the invariance and awareness of certain augmentations are task dependent. And then for this particular something task, it turned out that temporal information is critical. and then we provide a framework so that it naturally provides such encodes such information. And you may ask another baseline, which is that we do not perform temporal augmentation at all, and then that baseline was also much worse than our proposed baseline. Yeah.
But in the previous slides, you show without the temporal, you still have the 26 something, right?
Yes. So it's like a 5% or 4.5% difference.
So that means if I use a predictor to predict the Gaussian distribution, if that Gaussian distribution is zero mean, zero variance, I should get 26.5. How come I can get 10 something?
Because this already also have the other contrastive learning objective baked inside, right? Our baseline, the no encoding baseline. Whereas the baseline you described is just the only objective is trying to predict the temporal distribution, right?
So I still don't get it. So if
maybe we can talk after the meeting.
Okay, sure.
Right. So a kind of reminder is that the speaker only have 20 minutes left, and then right now it's only the first piece of work, and he has 2 more piece of works to go. So
I will. Thank you, and I will skip this side note. But basically, we try to investigate are there guiding principles on how to select wheels.
Chen, just let you know that you don't have to rush, and after 5 p.m. I'm not sure how many people will still be here, but if people are interested, they will live here and listen to your talk.
Sure, sounds great. And I think I will give it a try. Yeah, and for the speaker who just asked me questions, so I cannot see your face because this is I can only see my slides. So after the presentation, I'm happy to keep discussing that question with you. And for this, to wrap things up, we also investigated how are there guiding principles on how to select wheels. And the good news is that there are, and we proposed the information minimization objective. And then the bad news is that they are task specific. So it's unlikely that we have a self-supervised framework that works well for a super diverse range of tasks. So they have to, those different tasks, they have to share some underlying information for your learner representation to be effective. Okay, so second part of the talk is trying to do prediction and predict what may happen in the future. And it's kind of a little bit embarrassing, but I personally really like this ag problem. It's like I want to learn a function that takes in either pixels or a feature of an ag, and then take a word or a representation of an action like boil, and then I want to predict what may happen when applying that action to these objects. So in this case, it's a hierarchical ag. And then why I'm interested in this is it's a more compact representation for videos, and then which allows us to represent videos as object state transitions, and then furthermore we can do action recognition, object tracking, visual common sense reasoning, all by masking out different parts of this same function. Yeah, and basically I want to like I mentioned earlier, different ways, 100 ways to cook an egg. So why I'm interested in long video understanding, and I want to discover the key state transitions, which allows me to capture the key moments from a long video, and then for a concrete application can be video summarization, but you can also imagine that summarization can act as a compressing function to help us to encode longer videos. And then it's always good to have a structured representation with interpretable nodes and the graph, right? Like objects and their state transitions, their relations. And their state transitions is basically visual dynamics. And then future prediction itself can be important. such as the Waymo case, like we need to predict what may happen in the future in order to plan accordingly and in order for the car to drive safely. And how to predict the future, I think definitely I'm not among one of the first researchers who are interested in doing this from videos. And there are a lot of previous work which are great. And earlier work, they try to generate images, like work by Carl Wondrich and Tianfan Xue. They try to, given the source image, they want to predict what may happen in the future in terms of generated images. And for our particular purpose, maybe future image generation can be an overkill, right? After all, we are interested in structural representations. We don't need perfect reconstruction of every pixel of a video. And then, so that comes generating representations. There are also works, and you might be familiar. I think one of the most popular work in the last few years is the CPC, Contrastive Predictive Coding, which their original use case was trying to frame like image reconstruction and audio reconstruction as a like autoregressive task, and then you want to predict what may happen next. So is the problem solved? Not quite. Like so, all of them, they have some implicit assumptions, such as like if you want to predict at a fixed offset into the future, you need to deal with high uncertainty. Like for example, a very popular case is that for a ball that can go in many different directions, it's really hard to know with a limited amount of observation which direction the ball may go. And as a result, if you try to average the expectation of success or the likelihood of the pixel reconstruction, then you got learn the average seen a future predictor that the ball goes in all directions, right? We don't want that. And then a solution proposed by this paper is that they want the network predict several potential future outcomes. And then they take the minimum like error as their training signal, right? Just getting one of them correct is okay for this framework. And then you basically essentially encourage the model to generate more diverse outputs. And then the issue with this is that it's quite short term in the particular setup that paper demonstrated. They at most do a few seconds into the future. And then they also, their framework is also limited to simple low-level visual data like I'm showing here. So the ideal future predictor is something like this. Again, I apologize for those who are not interested in eating, but an ice cream example. So for this particular like ice cream example at time t, so I want to actually, I think the animation doesn't work. I want to go from this time t to time t plus 35 because that's actually like object state transition, right? From like some cream poured into ice cream machine to ice cream. And then you can see that B, C, D, they are all like future frames. And we don't know, like, because we don't have explicit annotation on the notion of future, we don't know which one is the correct future. Or like by correct, I mean the desirable future prediction that's corresponding to object state transitions. So we want our framework to be dynamic in terms of not requiring a fixed offset into the future. And then we also want it to be high level, such as similar to the feature generation case, like we want to capture high level semantic information in our representation, such as from mixing eggs and flour to rolling out dough or this cream to ice cream. And then of course, I mentioned that it's very ambiguous and difficult for humans to annotate such keyframes. So ideally we want our framework to be unlabeled, unsupervised. So here I'm showing an example. By the way, this is ICCV paper led by our awesome intern, Dave Epsa, so at UC Berkeley. And I think we take a concrete example here, like, so we have an instruction video, which we use as a starting point of our project because the temporal structure of instruction videos are more are easier to be captured because they are organized by steps, right? And then given such a video, we have some nodes. The visual nodes corresponding to the red dots here, they are like correspond to RGB frames or short clips. And then we also have the blue nodes, the text node, which comes from the ASR transcriptions. And then our training objective is actually a quite simple one. So we randomly pick an initial starting point, which can be a blue node or can be a red node. So in this particular illustration, we pick the visual frames as a starting point. And then we try to like go through find the corresponding representation in the other modalities such that they are mapped semantically. And it's worth noting that for illustration purpose, I'm showing a very clean example. And in reality, like the text and the visual frames, they may not be temporally aligned, but our framework will still work because this yellow edge, it doesn't take temporal offset into consideration. It just tries to maximize the semantic similarity between the two different modalities. So it can actually jump around in time. And then after we have such representation, we want to predict the future. Say the green arrow is already like an oracle, right? Which we know that from adding soy sauce to the chicken, then the next state corresponding to chicken is that chicken are put into like chili oil. And then suppose we can go to this something in the future. And we can then go do the same thing. Like we want to go to not only the future in a visual node, but also text node to obtain a combined representation. And then how to train this like yellow node and the green yellow arrows and the green arrows. I think for yellow arrows is kind of a standard cross-modal contrastive learning, like what's being done by a lot of work more recently, notably like Clip from OpenAI, right? You have paired information and you want to learn contrastive learning to learn representations that captures the semantic correspondence between the two modalities. But how to learn the green arrow, which we don't actually have the ground truth supervision? So our like intuition is just forming a cycle across a model cycle. And we not only use the temporal dynamics model to go forward in time, but also it should go backwards in time. And the ending point of this cycle should be as close as the starting like point of the cycle, which they should be, right? If the temporal transition is reversible. So why does this cycle consistency formulation work in practice in discovering key state transitions? So let's revisit this ice cream example. So I think from A to B, why it seems like a trivial shortcut, but why the model is prevented from taking this shortcut by like staying at the same location? It's basically like when we start the cycle, we do not know whether the green arrows does not know whether the input feature comes from the visual modality or text modality. Well, it's possible or it's trivial to just stay at the same location with respect to the visual location. For text, actually, we force the model to at least always look one step ahead. And then you can see that if we go to the next sentence, which is not at time t+1, but time t+22, it's actually quite different, right? And then this actually prevents the model from staying at the same location. And for the time at t+22, why our model cannot establish the correspondence, or because like there's actually no relation tying the two frames together if you ignore the green ball that just show partially in the first frame. So if there's no link between the two frames, there's no way our temporal visual dynamics model to capture their correspondence, right? Similar to the shortcut provision for B. And then naturally, D will be an easier case for A to go forward and backward, right? And then this is our intuition why our cross-modal cycle-consistent objective leads to discovery of longer-term keyframe, key object state transitions. And implementation-wise, I think we do not use a transformer in this case. We just use soft attention so that everything is differentiable. So you can see that first we we start from this visual encoder, and then we try to use attention to softly pick the corresponding text representation, which corresponding to add soy sauce. And then we try to use our temporal dynamics model, which is G forward, to predict forward in time. And then we then try to retrieve the corresponding future frame among all the visual node candidates and use attention to retrieve the future, which is this chicken into chili oil. And then if you flip this diagram horizontally, then you basically got the same formulation for how to going back from this for our framework. And then there are some details to avoid shortcuts. I will really quickly introduce them. So one intuition, how to select starting nodes, or more likely how to avoid trivial starting nodes, is that we use the cross-modal correspondence as a signal to pick more meaningful keyframes. For example, in this case, when we do cross-modal retrieval, it has a high activation on the rinse off scallions, then it's likely to be a good starting node. Whereas in this particular case, you can see the distribution is quite uniformly, and then indeed this is just a talking head. It doesn't really correspond to any key state changes. And then we also add some basic constraints, like for the visual node, and more importantly for the text node. We don't want the model to either stay at the same location or going backward in time. Note that these constraints are only used during training, because during test time, we don't have available the temporal signals. We just want the model, the G function, only aware of, okay, it needs to predict forward or backward in time. If no questions so far, I will show some results. Our model.
Actually, I have a question.
Sure. Yes.
So from the let's say I want to see the relationship of your work with the Taylor expansion. So basically, in the mathematical, if you have a Taylor expansion, you know the starting point and you know all of the derivative, first order, second order, and very high order. You can do precise prediction all the time, right?
You mean treating video as a super high dimensional input signal?
Signal. So I wonder, have you done any analysis about, in your model, is your model is pretty good to estimate the first order or second order of the derivative in the high dimensional space, and probably has a problem in the very high dimensional, so very high order derivatives, and such that you can, in some durations, you can do pretty good prediction.
I'm not sure. I think it's a topic we should go into details later on, but my immediate thought is that I'm not sure how to handle the super high dimensionality of those video pixels. And not only it's high dimension, it's also quite noisy, right? If you shift the pixels by 1 pixel, then the entire signal is messed up, right? And then you want to use a neural network to learn a representation of such frames. And then the question becomes, okay, if you already learned such a representation, how to properly analyze such learned representations with neural networks? So I don't have a good answer for either question. I'm not sure.
It should not be on the pixel level. So you have for every frame, you have a representation vector, right?
But that representation is already jointly trained with the home framework. So it may already throw away a lot of the high frequency signals or subtle details in the visual domain, right? Because it's motivated it has an information bottleneck, which is a 2000 dimension feature vector. And then it needs to do a lot of stuff, such as picking the nearest.
I'm talking about the derivative. It's not derivative. over the features. It's the derivative over time. So the derivative of features over time.
Yes, I'm
So
not sure.
Okay.
I think my question is for you, which I think we should discuss after the meeting, is that I'm not sure whether the information is lost when I encode the pixels into the representation, or when I try to learn such my prediction model. So that's something I'm not sure. And
okay.
I'm not sure.
Okay.
Yeah. So some examples, like I think the paper is online, so you can like watch we also have a video, but basically our model is able to successfully pick given the start node, is successfully to go to the other modality, like corresponding to DOE in the first example, and then predict forward in time in both modalities, like place a bow, DOE in the lightly greased bowl, and then got the corresponding visual feature, and then go backwards. And then it can also start from the visual pixels to text, and then forward in time. And it can also discover the key state transitions, which I really like, because I want to use this model to summarize super long videos. And then you can see that at least for instructional videos, the model indeed is able to discover such transitions in cooking videos. And by the way, I'm not sure if I mentioned, so the training data and all the visualizations come from is the cooking or kitchen subset of the How to 100 million data set. And another cool application is that once you have a forward prediction model, you can actually use that to measure the compatibility of two pairs of frames with respect to forward in time. And then you can use that to temporally order a collection of images, right? And I think here are the reconstructed frames, and under them is the ground truth temporal index. So I think for the first example, it's basically a perfect reconstruction. And for the second one, it messes up the first 3 frames, but they are visually quite similar. So I think I would still consider this to be pretty good result. And then, of course, like I mentioned when discussing the future prediction, the visual encoder is learned, and it's learned in such a way to capture temporal dynamics and high-level semantics. So you can always try to inspect the individual neurons, which some of them corresponding to objects and others may corresponding to actions. Okay, for the visual language navigation, I will give a 2-minute overview, and then if people are interested, I can still like go into details. So it's basically trying to like solve this visual navigation task, where the input is a virtual environment. You can take actions and explore, and then a task is defined with respect to human natural language, right? And then I feel it's a perfect task for multimodal representation learning, because you have a lot of modalities, like at least visual and language, but if you have more sensors in the agent, then you have more modalities. And then I think it's a natural bridge to go from passive observation, in my case, our videos, to active exploration. And then hopefully the agent is able to learn in both scenarios. And then I want to, for this particular ICCV paper, I want to advocate the transfer learning game, or like not end-to-end learning. Like I want to advocate that there are certain information that should be taught to an agent before it enters an environment, such as language and object grounding, right? So those shouldn't, in my opinion, learn from scratch in the target environments, because it's prone to overfitting. And then the agents, they should always, in my opinion, encode some of the common sense information in their brain or in their neural networks, right? And in this particular work, we try to learn visual language representations to map the natural language description into a like mid-level intermediate representation of language. It can be in this form like functions. It can also be logic functions or logic forms, right? And then I want to argue that this can be pre-trained without depending on a specific environment, right? So this is the language common sense. When we human try to execute a task, we can imagine like how to execute it without tying it to a specific room, right? A specific campus or office. And this like intermediate representation many times is often easier to collect, so you can train at a bigger scale. And then focus 2 is actually a byproduct. Like I use transformer encoders, and then I want to encode long-term dependencies in terms of the visual observations and language observations. And you can see that here are the examples where the blue arrows are where the instructions corresponding to the visual observations locally within that certain time step. But then there are also like certain instructions that requires a long-term memory to refer back what happened before. Then I want to go into the details, and you can imagine this is just a video bird or whatever transformer, but instead of taking video and text as input, it takes input language instructions, camera observations, and then optionally previous actions taken by the agent. And then again, I won't go into the details. So we explore some of the pre-training and joint training, basically trying to map the language encoder, trying to learn encoder-decoder on this natural to synthetic language or instruction translation task. And then this language encoder can be transferred to our joint framework here. Right? And we show that I think a few key takeaway knowledges. First, transformer is helpful. I'm not sure it's always the case, but for this particular data set where it requires long horizon temporal reasoning, it's actually very helpful. And then to demonstrate this, we actually did ablation, where we try to ask the agent to do the full task from scratch, which consists of, I think the horizon length is typically 50 actions. Compared to like just addressing the sub-goals, where we try to initiate the agent into the desired state by following the demonstrations, and then ask it to execute a sub-goal, which is typically 7 steps. And then you can see that LSTM and our proposed method, they both are good at like encoding the sub-goals, solving the sub-goals. But when it comes to the long horizon task, our transformer-based model actually has a, I would say, significant improvement over the LCM baseline. And we also did some of the ablation on the how long the memory to encode, and the longer, the better, I think, the take-home message. And another interesting idea is that the benefit of using the intermediate representation. So we compare our language encoder with a language encoder like trained end-to-end with the target environment, which corresponding to the first row. And also off-the-shelf Wikipedia trained a BERT encoder, and our like pre-trained encoder, which maps human instructions into the synthetic representations. And we can see that there's a significant improvement for both seen and unseen environments. And I don't know why, but maybe it's a domain mismatch, but the pre-trained BERT performs even slightly worse than like training from scratch. So I think those are like the key takeaways of this paper. And then of course we compare with previous SOTA on this particular benchmark, and we achieve better performance. And then here's a particular visualization I'm interested in, where it's trying to highlight, show the attention heat map when trying to solve the task given the current observation, like the agent is holding an apple, but then the task is trying to bring the apple back to the microwave. And then you can see the frame that's with the highest attention heat map corresponding to this microwave. So it's doing something, right? We know that the attention memory or the transformer itself serves as a memory to solve this task, to capture long-term temporal dependency. Okay, so a summary, like I'm interested in video understanding. I'm particularly nowadays interested in learning from unlabeled videos. And then in this talk, I briefly talk about a few steps towards a video understanding roadmap, like learning scene representations, learning temporal dynamics, and transfer the representations to an agent. And then I think everybody, a lot of us, like the audience, including also myself, we're interested in like learning using going from manual annotated data to such automatic supervision. Maybe the automatic supervision is unsupervised or self-supervised, like the contrastive learning for images or for video pixels themselves. But some of them are metadata, like the titles of the web videos or captions of web images. And some of them may be just cross-modal correspondence within the data itself, like video is a good example, right? And then I want to advocate that video is a rich source of automatic supervision. You not only get the language and vision, but you also learn about the shape deformation, state transitions, which I personally feel are very important. And the next steps, I'm personally interested in going even early in the roadmap, that going from scene level representations to objects and relations, also without explicit supervision. So we need to have a mechanism to discover the notion of objects. Probably I feel that video, by observing objects move, is a useful learning source for such applications. And then another thing probably I'm going to do with my student at Brown is to build better interpretable, more efficient models, because we don't have industry level computational resources, but there are still a lot of interesting stuff we are working on. Okay, so here are my collaborators, and thank you so much for listening, and thank you so much for the very interesting questions, and I hope I'm able to address some of them. I'm happy to have more questions if there's any. Thank you so much.
Thank you for the great presentation. Chen, do you mind if we have a few more questions to discuss here?
Of course.
Okay.
Go ahead. I'm not sure if I now stop share.
Any questions? Okay, I do have a question on your first part. So, the work on compositional augmentations for videos. And do you have any comments, ideas on applying the ideas for image self-supervised learning? Because you have the crop which capture the spatial information, right? So I guess maybe a very special case of your method would be applied to image self-supervised learning.
I think that's a great question. And my honest answer is that I have tried that and it doesn't work on ImageNet. And it works on synthetic environments such as Clever, where it actually needs to tell the locations of those different objects in order to solve certain tasks. But for ImageNet, my personal guess is that the existing set of data augmentations are already pretty well engineered for this particular downstream task, so that if we try to turn some of the invariances into awareness or equivariance, that may actually hurt the classification performance if that's the only task we are interested in. But on the other hand, I can imagine that maybe some form of our formulation may be helpful for object detection, for example.
I see. Thank you. Thank you for letting me know the results.
Yeah, and may I have the name of the
Inpen had a lot of great discussions.
Yeah, I'm here.
Yeah, sorry. Yeah, I didn't see your face or didn't see your name during my presentation. Yeah, thank you for the great comments. Yeah.
Did you see me?
Yes, I can hear you.
Hey, it's a very nice talk. So the major question, so for the dynamic temporal stuff, I assume when you do the prediction, you predict the representation for the frame you want to predict, and then use that representation vector to predict the label or predict the text. which is considered as the final result, right? Okay, so let's say your every frame, time frame t, you have a representation. Let's say this is the xt. Let's say it's a maybe it's a 256 or it's a 50. It doesn't matter. It's a vector, right? So this is a vector. Let's say this is a xt and xt plus 1 until xt plus 22. You did the prediction, which is awesome. So, and if we do this as a Taylor expansion, so basically you can do xt plus delta equal to xt plus first derivative multiplied the delta, and second derivative multiplied by 2, divided by 2, and multiply the second order of derivative. And we do the Taylor expansion on this vector. Then you can do, so as long as you have the first order of derivative, second order derivative, third order, until unlimited order of derivative, you can always have the exactly accurate prediction for each frame. So I'm curious about is if so which derivative your model can accurately predict allows you to do very good prediction over the time slot. So let's say, hey, your model has a very good prediction on the first order, and then you can second order and third order. So this does allow you, so this is the support your model can do prediction for a fair time duration.
I think that's a great point. Is that something related to slow feature analysis? I'm not sure if that's the term, but I think it's a good analysis. I think we can run like on our trained model, how good it is in terms of estimating the sequence of the video features. Yeah. I think it's something we need to try.
And another reason I mentioned this, I have a feeling this may support why your cycle model works, because once you try to estimate the derivative, and because this is not just xt minus x plus 1 minus xt divided by the delta t, you have a model to model that. But if you estimate the derivative from both directions, will be more accurate than estimate from one direction. So then so if you can show the one direction, the derivative is not significantly worse than both dimensions. So this support your motivations, right?
I think I got the high level intuition, but my brain isn't as efficient as I wish to be. So I would need to think more, and it would be great if you have some pointers. If you could share with me, then that would be awesome. Yeah.
Okay, great. Anyhow, this is my question. Thank you very much for your talk. That's a great talk.
Yingpeng, if you need the contact of our speaker, you may reach out to me, or I can share the email.
Thank you. I may not have my kids already there. Sorry.
Thank you for the question.
Thank you very much.
Any more questions from the audience? We may still have time to do 1 or 2 more questions. If not, we may close the meeting today. And thanks again. Let's thank our speaker again. And I guess everyone enjoyed the presentation. And if you want to discuss with our speakers, you may reach out to me to get the contact, or directly reach out to our speaker. And some of us will have the one-to-ones with our speaker tomorrow. I hope Chen, you will enjoy the one-on-one discussion tomorrow. And have a good evening.
Okay, thank you.
Thank you, Chen.
Thank you.
Bye.
Thank you.
Thank you.
Thank you.